Hello viewers, we want to continue with our lecture series on physics, and the topic for today is physical quantities. My name is Dr. Godwin Obono. In case you're new to this channel, please subscribe, turn on the notification button so that when new videos are made, you'll be first to be notified. Also, if you find value with this video, please share and like the video. Let's begin. Physical quantities are those parameters in physics that can be measured. Example, time. For instance, we can determine the time of the day with our clock. That is to say that time can be measured by the use of a clock. Mass, for instance, is another physical quantity that can be measured by the use of a beam balance. Distance, for instance, can be measured with a meter rule. And all these physical quantities can be measured or determined by one instrument or the other. For this reason, they are called physical quantities. They are basically divided into two. Number one, we have what we call the fundamental quantities. And number two, we have the one we call the derived quantities. Derived quantities. The fundamental quantities can also be called the basic quantities, basic physical quantities. Let's begin with the fundamental quantities. Like I told you, there are two quantities. The physical quantities are divided into two. We have the fundamental quantities or the basic quantities, and we also have the derived quantities. It will interest you to know that in physics, everything that makes up physics, the body of physics, it's simply physical quantity. So the fundamental quantity can be defined as those quantities whose units cannot be expressed in terms of other quantities. What that means is this, that the unit of each of these quantities we cannot possibly derive the units of this quantity. So for instance, mass, which is of course an example of a fundamental or basic quantity, the unit of mass is kilogram or gram. It means that mass, the unit of mass, you can identify mass by what? Kilogram or gram. Time, for instance, the unit of time is in seconds or minutes or hour. Length is another example of a basic quantity. Sometimes you say length or distance. The unit is in meters or centimeter. Temperature, the unit of temperature is in Kelvin or degrees Celsius or Fahrenheit. Current, the unit of current is in amp. Amount, also known as a mole, the unit is in mole. Luminous intensity, the unit is in candela. These units are very important because they tend to give us the identity or describe the identity of these basic quantities. So there is no one that can explain possibly why mass has the unit kilogram, why time has the unit seconds. This is the reason why we said they are basic quantity. They are fundamental quantities because their units cannot be derived. Their units cannot be expressed in terms of other quantities. So all you need to know is just that the current has a unit in amp, that the amount of a substance has a unit in mole. There is no further explanation as to the origin of this unit. This is why we say that these quantities are basic or fundamental quantities. By the time we discuss the derived quantity, you'll see that these are quantities whose units can be derived. That's why they are called derived quantities, because their units are derivable. Now it's important to know that apart from these quantities, every other quantity in physics are all described what as derived quantity. So if you begin to think of velocity, acceleration, force, pressure, every other quantity that is not among these ones are all derived quantities. And for them to be derived, it means that all their units are all derivable. So for every physics student, it's important that these basic quantities must be known. The unit must also be known as well, because I've given you two types of units. Now this is always called the SI unit, systemic international, and this one are called the Gaussian unit. So the units are basically divided into two. We have the SI unit and the Gaussian unit. So it means that the length or distance has the SI unit in meters and the Gaussian unit in centimeter. So let's take these derived quantities now, so that you have a better understanding, because by the time we discuss derived quantity, you should be able to compare with basic quantity and there will be absolute understanding. Derived quantities are those quantities whose units are derived or derivable. So it means that there is always explanation as to why the unit of any quantity so-called derived, why it is called that way. So everyone must give an explanation as to why the unit of velocity is what it is. So we will take example of each of these derived quantities. We'll tell you how the units are all being derived. Now let's take the first one, velocity. Velocity, always designated by the letter V, is always equal to. Now for you to know the unit of velocity, it's important for you to know the formula of velocity. Normally, velocity is the ratio of displacement toward time. That means displacement all over time. So if you need to know the unit of velocity, remember we said that the unit of velocity is a derivable unit. And if it is a derivable unit, then we have to explain how it's been derived. So for you to do so, you have to remember the formula for velocity, which is why I said velocity is the displacement upon time, or displacement all over time. Now in this context place, it's important for you to know that displacement is also seen as distance, and of course displacement is the same as a basic quantity. And so if we are looking at the unit now, the unit of velocity, we will say that the unit of the displacement, which of course is meter, all over the unit of time, which is 1 second. So we now say that the unit of velocity is meter per second. You see that this unit is a derivable unit. We were able to explain how this unit came about from the formula. So it means that for all derived quantities, there is just no way you can get their units except by recalling or remembering what their formulas. Now this is velocity. Let's take another one, acceleration. Acceleration. We want to know the unit of acceleration. For you to get the unit of acceleration, you must remember the formula of acceleration. Acceleration is defined as the ratio of the rate of change of what velocity. It means that acceleration is defined as velocity all over what time. But in this context, at this point, it's important for you to ensure that everything that makes up acceleration are all fundamental. Now, because based on this, V all over T, you see that T is a fundamental quantity, but V is not a fundamental quantity. So because V is not a fundamental quantity, you have to substitute V and bring in its equivalent that will make this formula become totally fundamental. So we will now say, therefore, that acceleration is equal to, instead of V, we're going to have D all over T, where D all over T represent what velocity, and again divided by what T. Remember that the original formula is V all over T. And so where V here is D all over T, like I told you earlier, D is displacement, while displacement all over D represent displacement. And now displacement all over T divided by what T. This will eventually become D all over T squared. That means Acceleration is the rate of change of displacement. In other words, displacement all over t square represent acceleration, or velocity all over what? The time. Of course, you know that this is simply what the formula, but we are not interested in the formula. What we are interested in is the unit. We want to explain how the unit, how we could get the unit of what? Acceleration. So we can now say that A is equal to, now having transformed this formula to this formula, we can now say that everything here are all what? Fundamental. Remember, the idea is that everything that makes up a formula must all be fundamental, must have fundamental quantities totally. Unlike from here, V all over T, we say V is not a fundamental quantity, so we have to replace V with its equivalent, which is what? D all over T, and this led us to D all over T squared. And so at this point, we will ask ourselves, what is the unit of D? The unit of D is M, is meter, all over the unit of T, which is what? Second. And in this case, second, which is the time is raised to power 2. Because T is raised to power 2, this second must equally be raised to power 2. And this is therefore called meter per second square. You can see that we have derived the unit for what? Acceleration. That's why we said all these quantities are derivable, because their units are expressed in terms of other quantities. You can see the unit of acceleration, which is meter per second square, is expressed in terms of what? Displacement and time. Now let's take another one. Let's take force. Force. For us to know the unit of force, we must remember what? The formula of force. Force is defined as mass times acceleration. Mass times acceleration. So now again, mass is a fundamental quantity, but acceleration is not a fundamental quantity. What do you have to do? You have to substitute acceleration. So we can now say that this is equal to M. You replace A. As if you're replacing A, you have to bring in the formula of A, which is V all over T. Even when you have substituted acceleration with V all over T, it has not completely turned everything toward fundamental quantity. So the problem here is what? With the V. And so again, we will replace the V. And so we say this is equal to M times D all over T squared. Remember we said earlier that acceleration is V all over T, acceleration is D all over T squared. So we'll rather go with this one, because this formula has everything fundamental as fundamental quantities. So we now have M, which is mass, times D, which is displacement, all over what? T squared. At this point, we now begin to ask ourselves, what is the unit therefore for force? This will be equal to the unit of mass, which is kilogram, the unit of displacement, which is meter, all over, you follow the formula. The formula says divided by, and the unit of time, which is what? The second. And because the second is raised to power 2, this the time is raised to power 2, this second has to be raised to power 2. Hence, this is equal to kilogram meter per second square. It is this kilogram meter per second square that every physics student do call Newton. That means Newton is simply kilogram meter per second square. So in your examination, it's possible they will tell you that which of the following is true for force, and all you see there are what? Units, but you will expect to see Newton, but Newton might not be in any of the option. What you will rather see will be kilogram meter per second square. So that is force. Now let's continue with more examples. After force, let's take another example. If we take, for instance, moment. What is the unit of moment? Now you need to remember the formula of moment. Moment is defined as the product of force times distance. And of course, moment is the same thing as torque. Torque is the same thing as moment. So moment is defined, moment of a force is the product of force and distance. Now if you remember that moment is force and distance, then you begin to ask yourself, are everything fundamental? Remember, what makes up a formula must totally be what? Fundamental quantities. But in this case, force is not a fundamental quantity, though this is a fundamental quantity. So we'll rather simplify. We say moment is equal to, instead of F, we'll bring in the formula for force, which is what? Mass times acceleration, then times what? D. You have MAD. Now again, A is not a fundamental quantity. We substitute A. That gives us md all over t squared times d. So you now finally have md squared all over what? T squared. So the moment of a force is the product of mass and the square of what? Displacement all over what? T squared. And then when you now look at the unit, it has to be the unit of mass, which is kilogram, times the unit of displacement, which is of course meter. Because this displacement is raised to power 2, the meter has to be raised to power 2. You maintain the division sign, then the t is in second, and because the t is raised to power 2, the second has to be raised to power 2, and this is equal to kilogram meter square per second square. This is therefore the unit of what? Moment. Now, if you don't, this is what again you may call Newton meter. Newton meter, when you're taking the unit of force to be Newton, you now have Newton. Why the unit of D here is meter, and that's why we have Newton meter. But in exams again, they may say which of the following is true for moment of a force. And when you look all through the option, you will see that the options are having what are all what SI units, but the units for moment that you know might be Newton meter. You may not see it there. Rather, what you will see might be kilogram meter square per second square. So this is a unit of what? Moment. Which is why we said that these units are all derived. You can see we never derived the unit of fundamental quantities. I only gave you the unit of fundamental quantity because there is just no way you can offer explanation as to the origin or the source of the unit of fundamental quantities. But we can always explain or derive the units, how the unit of derived quantities. Having discussed the unit of moment, now there are two other quantities that are similar to moment. Not in respect to formula, but with respect to their unit. Now, take for instance, energy, work done. Then moment. These three physical quantities, derived quantities, three derived quantities have the same unit, but they don't have the same formula. Now let's see, I've explained for moment. We say moment is equal to force times distance, and we got the unit, and we said that you can have two units, Newton meter and kilogram meter square per second square. Now how about energy? Now if you look at energy, for instance, let's say this is energy, want to find the unit of energy. Remember that energy can either be what? Kinetic energy, or it can be what? Potential energy. Whether it's potential energy or kinetic energy, the unit is always the same. Of course, you know the unit is in joule. Now let's see, let's confirm that. Now if we take for instance kinetic energy, you know that kinetic energy is half mv squared. That's the formula for kinetic energy, half mv squared. Now half mv squared, now 1 all over 2 is not a quantity, it's a number, and all numbers do not have units, and so we will therefore forget 1 all over 2, and so what we would rather have would be what? mv squared. Now mv squared, the m here of course represent mass, but the v and the v represent velocity. A velocity itself is not a fundamental quantity like we have always done. We say this is equal to m, velocity itself is d all over t, and now because the v is raised to power 2, the d all over t has to be raised to power 2, and this will give us m d square all over t square. The unit therefore becomes kilogram, which is the unit of mass. The unit of displacement, of course, is meter, and because displacement is raised to power 2, this has to be raised to power 2, now divided by what? The unit of t, time, is second, and because the second is raised to power 2, this because the time is raised to power 2, this second has to be raised to power 2, and that gives us what? Kilogram meter square per second square. And you see that this is the same unit we got when we treated moment. Though the formula of kinetic energy is not the same as the formula of what? Moment. But then at the end, the unit is the same. Now, again, I want to emphasize that kinetic energy, whether kinetic energy or potential energy, we know that the unit is in joule. That joule is this. So that means kilogram meter square per second square is the same thing as what? Joule. It's the same thing as joule. Now, potential energy, the unit is also in joule. But why? The potential energy formula is different from the formula of kinetic energy, but yet both kinetic energy and the potential energy have their units in joule. Why is it so? The reason is, if you look for the kinetic energy unit in terms of the kilogram meter per second system, that's the unit in terms of kilogram meter second system, which is what we have done, you will see that the unit will be the same as the unit of potential energy also when you express it in kilogram meter second system. So what? Let's confirm that. Now, potential energy is always mass times gravity times what? Height. Now, this simply tells us that if you do not know the formula of quantities, there's just no way you can get their units. So you must, as a physics student, you must be you must have firm grip with your physical quantities. Now, for potential energy, the formula is mass times gravity times height. Now let's now ask ourselves, everything here everything that makes up potential energy, are they all fundamental? No. The answer is no. This is fundamental, right? This is fundamental, correct? But G is not the fundamental quantity. G is a derived quantity. Of course, you know that G represents acceleration due to gravity, and acceleration due to gravity has the same unit as what? Normal acceleration or linear acceleration. Though both will be different in terms of direction, but the unit is the same. So we can say, therefore, this is equal to the mass acceleration due to gravity, which is the same thing as acceleration in terms of unit, is d all over t squared. We treat it as the same as what? Acceleration, and then times height. This is therefore equal to the unit of mass. We begin to ask ourselves, what is the unit of mass? Is kilogram. The unit of d is what? Meter. The unit of height is meter all over, because of this division sign. The unit of t is in second, and because the t is raised to power 2, the second has to be raised to power 2, and this is equal to kilogram meter square, because m times m, that will be what? M square. Then all over was second square. You see that this is the same as this. Again, the formula of potential energy is not the same as the formula of kinetic energy, but you have seen that the unit in terms of the kilogram meter second system, you listen to it, kilogram meter second system, that means it's a system where the unit must have kilogram there, meter, and second. And so when you simplify when you work the unit of potential energy, you will see that it is kilogram meter square per second square. The same thing that goes to the unit of kinetic energy, and both are what? The same. And so when we say that the unit of kinetic energy or the unit of potential energy, we said it's in joule, we meant to say that their units are the same when you express them in terms of kilogram meter second system. So you can see that the unit, the SI unit of kinetic energy and potential energy are the same in terms of the kilogram meter second system. This is why we also could say that the unit of potential energy and kinetic energy is also in joule. Similarly, the unit of moment of a force and that of kinetic energy or potential energy are the same if you express them in terms of the kilogram meter second system. We can also see that for work done. For instance, work done is expressed as the product of force and distance. When you look at the formula of work done, it is force times distance, just like moment. Now, force itself is mass times acceleration, then times what? The displacement. Now, when you further simplify, you can see that acceleration is not a fundamental quantity like we have always said. What we have to do at this point is to substitute acceleration with its formula. If you do that, this will be equal to mass times acceleration, which is velocity, all over what? T times what? The displacement. Further simplification will give us mass times displacement all over t square, where displacement all over t square represent what? Acceleration, and again times what? The d, which is this other displacement or distance. And then when you further simplify again, this will give you mass times d square all over t square. Finally, in terms, if you bring in the unit, if you substitute these quantities with the units, remember that m here represents mass. And so the unit of mass, of course, is kilogram. The unit of the d here, of course, this d represents displacement on one hand and also distance on the other hand. But they both are the same when you consider them in terms of their unit. And so the unit of d here is what? Meter. Where since the d is raised to power 2, the meter has to be raised to power 2, then all over what? Second. Where the t is raised to power 2, therefore the second here has to be raised to power 2. And so this now becomes kilogram meter square per second square. You can see the unit here, this unit, kilogram meter square per second square, is the same as the unit of moment and is also the same as the unit of what? Energy. Which is why I said earlier that the unit of moment, the unit of energy, and that of work done are all the same in terms of kilogram meter second system. Let's also look at other physical quantities like the momentum and the impulse. You will see that momentum and impulse both have the same unit. Now let's look at momentum. Momentum, what is the definition of momentum? Momentum is equal to mass times velocity. So we can define momentum as a product of mass and its velocity. Now, further simplification, this will give us mass d all over t, where d all over t represent what? Velocity. But why is it important that you further simplify it? It's because we want to make sure that everything that makes up momentum are all fundamental quantities. Which is why we have to say that d all over t should represent velocity, where d is a fundamental quantity and the t is a fundamental quantity. Now at this point, we can now look for the unit. The unit of mass here, of course, is kilogram. The unit of d is meter. The unit of what? T here is second. This is equal to kilogram meter per second. And this is said to be the unit of what? Momentum. Also, sometimes you can say that, like I told you earlier, that the unit of momentum is the same thing as the unit of what? Impulse. Let's confirm that. What is impulse? The formula of impulse is Ft. That's to say, impulse is defined as a product of force and time. In terms of formula, impulse is not the same as momentum. But at this point, we have to simplify Ft to ma times t, where ma represents the formula for what? The force. We further replace acceleration with d all over t square and then times the t here, where d all over t square represents acceleration. And so this will give us md. Remember that one t cancel here, this t cancel, this one of the t is here. You'll be left with md all over what? T, and this is equal to, in terms of unit, kilogram. Then the d here has a unit of what? Meter, and the t here has a unit of what? Second. You also have kilogram meter per second, which is the same as this. You can say that the unit of impulse and the unit of momentum is the same. Sometimes you have that as examination question where they will tell you that which of the following is true of momentum. They will tell you, they give you a number of options. It could be in terms of the unit, and you see that the unit that you find there may be kilogram meter second per second. Now, another quantity that is very important for you to know as a physics student, the unit is power. Power, surface tension. Power, surface tension, viscosity. So, if you want to define or we want to find the unit of power, you need to remember the formula of power. Power is defined as the force all over one area. So you can see that each time we want to find the unit of any quantity, we must remember the formula of that quantity. So now power is equal to force all over area. We further simplify it. Force is mass times acceleration. All over what? The area. The area is usually length times breadth. I know there are different formulas for area, but basically the fundamental formula for area is length times breadth. And so this is equal to, again remember that acceleration is not a fundamental quantity, mass is a fundamental quantity, length is a fundamental quantity, breadth is a fundamental quantity. So we only have trouble or problem with what? The A. And so the A has to be substituted. And so this will be equal to mass, as the A itself is d all over t squared. And remember that this is divided by, which is this division sign, length times breadth. And this is equal to, of course, at this point we can substitute. We may decide to replace all of this with what? The units. Now the unit of m is kilogram. The unit of d here will be what? Meter. All over the unit of t here is second. And because the t is raised to power 2, the second has to be raised to the power of 2. Of course, we will retain our division sign. The unit of length is meter. The unit of breadth is meter. So we're going to have at this point kilogram meter all over second square, now divided by meter square. And if you further simplify this, you will have, if you simplify this further, we can say that power is equal to kilogram meter per second square times. Now we are replacing the division sign with a multiplication sign. Of course, you know that the fraction after the division sign is divided by 1. So if we are replacing the division sign with a multiplication sign, of course, mathematically, the 1 will come up while the m squared goes down. And so we're going to have 1 all over what? M squared. Of course, here now m will cancel itself here. It will take out 1 there. And then this will be equal to kilogram all over second square times what? M, because there's 1 m left there. And this is equal to kilogram per meter per second square. This is the unit of what? Power. It is this unit that we call watt, because the other unit of power that most students are aware of is the watt. So a watt is equivalent to kilogram per meter per second square. Very important. So you can see how significant it is to know the units of these quantities in terms of the kilogram meter second system. Now, please, let's take another one, surface tension. Surface tension is defined as force all over length. So you see how important it is. The formula must be remembered. Force all over the length. And so further we simplify, we got to simplify this further. When we do so, this of course has to be equal to mass times acceleration all over what? The length. This is equal to mass, acceleration itself has to be d all over t squared. And we are dividing this by what? The length. This has to be equal to m, this has to be equal to the mass times the displacement all over t squared. Remember that this length is the same thing as L all over 1. If we introduce a multiplication sign, the 1 goes up, the L goes down. And this is equal to m d all over t squared times what? The L. Now in terms of the unit, the SI unit, in terms of the unit, we therefore say that surface tension is equal to the unit of mass, in this case, will be what? Kilogram. The unit of displacement, meter, all over the unit of the time, second, and it has to be second square. There's a unit of this length, which is what? Meter. Of course, this meter will cancel this meter. You will now have kilogram per second square. Now, kilogram per second square, therefore, becomes a unit of surface tension. And this is the same thing as Newton per meter. Remember, if you are taking it from here, you can also say that the unit of force is Newton all over the unit of what? Length, which is meter, and that is Newton per meter. So Newton per meter is the same thing as kilogram per second square. So I leave it for you to go and find out the unit of viscosity. And if you have comments, if you have any problem, please go to the comment section of this go to the comment section, drop your comment there. I will respond. Again, please subscribe to this channel so that more videos that will come, you'll equally be notified. For that reason, turn on your notification button. You also share this video if you find it of value to you. Thank you.